Good morning, everyone. In this chapter, we study the data link layer, which focuses on one important goal, making communication reliable even when the underlying link is unreliable. All right, everyone. Now imagine this for a moment. The physical layer is like a worker who only knows how to throw raw bits at you. Zeros and ones, nonstop. No explanations, no organization. On the other hand, the network layer is a very demanding boss who says, I want clean packets, properly arranged, and on time. So who handles this situation? That's where the data link layer comes in, acting like a responsible middle manager. Its main job is to take the raw bit stream coming from the physical layer and turn it into a reliable, organized link for the network layer. This layer sits at layer 2 of the OSI model, exactly between the physical layer and the network layer, so it has to keep both sides happy. When the network layer sends a packet, the data link layer politely says, "Don't worry, I'll take care of this," and wraps that packet into a frame by adding addresses and error-checking information. Think of it like packing an online order into a box, adding the shipping label, and making sure nothing breaks on the way. Then the frame is passed down to the physical layer, which again goes back to speaking in its favorite language, bits. Now, the data link layer also offers different services. Sometimes it sends data without waiting for confirmation, like dropping a letter in a post box and hoping it reaches safely. Sometimes it asks for acknowledgement, like WhatsApp showing double ticks, and sometimes it sets up a full connection first, like making a phone call to be absolutely sure the message is delivered in the right order. So in short, students, whenever data moves smoothly and correctly between two directly connected devices, remember that the data link layer is quietly doing all the hard work, without complaining, just like a good teacher. All right, class, let's slow down and understand this slide properly, because this is the heart of the data link layer. Think of the physical layer as a very honest but careless worker. It sends bits exactly as electrical or optical signals, but it doesn't care if some bits get lost, flipped, or mixed up. Now, the network layer upstairs is very demanding. It wants clean, well-organized data, not a messy stream of zeros and ones. So who handles this pressure? Yes, the data link layer, the middle manager of networking. Now, the data link layer faces 3 core challenges. First is framing. Imagine your friend sends you one long WhatsApp message without spaces or punctuation. Good luck understanding it. Similarly, the physical layer sends a continuous stream of bits. The data link layer must break this stream into meaningful chunks called frames, clearly marking where one frame starts and ends. Without framing, the receiver wouldn't know which bits belong together. Second comes error control, because real-world links are noisy. Signals get disturbed by distance, interference, or even bad cables. So bits may flip from 0 to 1, like a student copying answers wrongly in an exam. The data link layer adds extra information so the receiver can detect errors and sometimes even correct them or ask for retransmission. This ensures data integrity, because wrong data is worse than no data. Third is flow control. Imagine a fast speaker talking to someone who writes very slowly. Chaos. Similarly, a fast sender can overwhelm a slow receiver. The data link layer controls the speed of transmission so the receiver's buffer doesn't overflow. It politely tells the sender, "Slow down, I'm still processing." So overall, the data link layer acts like a disciplined traffic police officer. It organizes raw bits into frames, checks for mistakes, and controls the flow so communication remains smooth and reliable. First, let's answer the basic question: what is framing? Framing is the process of taking a long, continuous stream of bits coming from the physical layer and breaking it into small, meaningful packets called frames. Each frame has 3 parts: a header, control information; a payload, actual data from the network layer; and a trailer, usually for error checking. Think of framing like packing items into labeled boxes so the receiver knows where one box ends and the next begins. Now let's look at how frames can be created. 1. Byte count method ***. Here, the sender puts a number in the header that says, "Hey, this frame has 5 bytes," or "This one has 7 bytes." The receiver simply reads that many bytes and assumes the frame is complete. Simple, right? But here's the problem. Imagine a delivery label gets smudged. If even one bit in the count is wrong, the receiver loses track of where the frame ends. It's like reading the wrong page number in a book. You're lost for the rest of the chapter. 2. Flag bytes with byte stuffing ***. In this method, special flag bytes mark the start and end of a frame. A common flag value is something like 0x7e. Now the question is, what if the same flag appears inside the data? Solution: byte stuffing. If the data accidentally contains the flag byte, the sender adds an escape byte, ESC, before it. The receiver knows, okay, this flag is not real, it's just data. Real-life example, like saying, I'm quoting the word stop, not actually stopping. 3. Flag bits with bit stuffing ***. Instead of bytes, this method works at the bit level. A special bit pattern like 011111110 marks the frame boundaries. If the sender sees 5 consecutive 1s in the data, it automatically inserts a 0. This prevents the data from accidentally look like a flag. At the receiver side, the extra 0 is removed. Think of it like adding a comma in a long sentence so it doesn't accidentally turn into a new paragraph. Physical layer coding violations. This is a smart trick. Some signal patterns are never used for actual data. So the data link layer uses these illegal patterns to mark the start and end of frames. It's like using a whistle in a classroom. Students never talk using whistles, so everyone instantly understands. Class has started or class is over. So in summary, framing is all about creating order from chaos. Whether we count bytes, use flags, stuff extra bits, or break physical layer rules, the goal is the same. Help the receiver clearly identify frame boundaries, even over noisy and unreliable links. Alright class, now we move to error detection, which is basically the data link layer saying, I can't stop mistakes from happening, but I can definitely catch them. Let's understand this slide step by step. The goal of error detection is simple. We add some extra bits, called redundant or check bits, to the data before sending it. These bits help the receiver figure out whether the data got corrupted during transmission. Notice something important here: detection, not correction. Fixing errors is expensive, so on relatively reliable links, it's cheaper to just detect the error and ask for retransmission. Think of it like checking your exam answer sheet for missing pages. You don't rewrite the whole exam. You just ask for a reprint. The simplest technique is the parity check. We add one extra bit so that the total number of ones becomes either even or odd. If the receiver counts and the parity doesn't match, it knows an error occurred. This works fine for single-bit errors, but if 2 bits flip, parity gets fooled, like 2 wrongs canceling each other out. Parity is cheap, fast, but not very smart. Next comes the checksum. Here, data is divided into fixed-size words, usually 16 bits, and all words are added together. The checksum is the ones complement of this sum and is sent along with the data. The receiver repeats the process and checks if everything adds up correctly. This method is widely used in internet protocols like IP, TCP, and UDP. Think of it as calculating the bill total. If even one item price changes, the total won't match. Now we reach the king of error detection, CRC. Finally, let's talk about CRC power. An R-bit CRC is very strong. It can detect all single-bit errors, all double-bit errors, any odd number of errors, and all burst errors shorter than or equal to our bits. In simple words, CRC is like a strict teacher. It catches almost every cheating attempt. So overall, error detection codes act like security guards for data. They don't repair the damage, but they immediately raise an alarm when something goes wrong, ensuring reliable communication over unreliable links. Alright everyone, now we move from detecting mistakes to actually fixing them, which is what error correction codes are all about. Think of this as upgrading from a security guard who only shouts error to one who says error at seat number 5, I'll fix it. The goal of error correction is to add enough extra information, called forward error correction, FEC, so that the receiver can recover the original data without asking the sender to resend it. This is extremely useful in noisy environments like wireless networks, satellite communication, or deep space links, where retransmission is slow, expensive, or sometimes impossible. Imagine you're watching a live cricket match on a bad network. You don't want the match to stop and say, please replay that ball. Error correction tries to fix things instantly. Next, we look at Hamming codes, a very famous and clever technique. Hamming codes can correct single-bit errors and detect double-bit errors. The smart trick here is that parity bits are placed at positions that are powers of 2, like 1, 2, 4, 8, and so on. Each parity bit checks a specific group of data bits. When the receiver checks these parity bits, it forms something called a syndrome. This syndrome is basically a binary number that directly tells us which bit is wrong. In the diagram, the checks fail and pass in a pattern that points exactly to bit position 5. That bit is flipped back, and boom, the data is corrected. It's like a detective who doesn't just say crime happened, but also says suspect is sitting in row 5. Finally, we have Reed-Solomon codes, which work on symbols instead of individual bits. This makes them extremely powerful against burst errors, where many consecutive bits get corrupted. That's why Reed-Solomon is used in CDs, DVDs, QR codes, DSL, and even space communication. Ever noticed how a scratched CD still plays music? That's Reed-Solomon doing its magic behind the scenes. So to summarize, error correction codes give networks the ability to heal themselves. Instead of panicking and asking for retransmission, the receiver calmly analyzes the redundancy, finds the error, fixes it, and moves on, like a very mature adult in a very noisy world. Alright class, now imagine this situation. You open a tap fully, but your glass is tiny. What happens? Water everywhere, table, floor, your marks, everything gone. Grinning face with smiling eyes, that is exactly the problem of flow control in computer networks. The problem? In networking, sometimes the sender is very fast and the receiver is slow. The sender keeps sending frames like a machine gun, but the receiver's buffer fills up. Even if the channel has 0 errors, frames still get lost simply because the receiver can't handle the speed. So the issue here is not corruption, it's overspeed. The problem? In networking, sometimes the sender is very fast and the receiver is slow. The sender keeps sending frames like a machine gun, but the receiver's buffer fills up. Even if the channel has 0 errors, frames still get lost simply because the receiver can't handle the speed. So the issue here is not corruption, it's overspeed. The solution? Feedback-based flow control. To fix this, we use feedback-based flow control. The receiver politely tells the sender, "Okay, I'm ready, send more," or "Wait, I'm still chewing." This is the most common approach at the data link layer. Protocol 1, stop and wait. This is the most disciplined student in the class. The sender sends one frame, then stops and waits for an ACK, acknowledgement. Only after receiving the ACK does it send the next frame. Think of WhatsApp voice notes. You send one note out box tray. You wait for seen eyes. Only then you send the next one. Very safe, very simple, but also very slow. Most of the time, the sender is just sitting idle, waiting. Protocol 2, sliding window. Now this is the smart multitasker. Instead of sending one frame and waiting, the sender is allowed to send multiple frames at once, up to a limit called the window size, W. In the diagram, W equals 4. That means the sender sends frame 0, 1, 2, 3 continuously. The receiver sends ACKs as it processes them. As ACKs arrive, the window slides forward, allowing more frames to be sent. This keeps the network busy and efficient, like a restaurant where multiple orders are cooking at the same time instead of one dish at a time. Stop and wait versus sliding window. Stop and wait. Simple, safe, but wastes time. Sliding window. Faster, efficient, keeps the pipeline full. Modern networks prefer sliding window because time is money and bandwidth is expensive. So remember, flow control is not about fixing errors. It's about not drowning the receiver. Because even in networks, sending too much love too fast can cause problems. Alright class, now meet the first hero of reliable data transfer, stop and wait ARQ. Simple, honest, and a little slow, like that student who raises their hand for every permission, grinning face with smiling eyes. First, what is ARQ? ARQ stands for Automatic Repeat Request. The idea is very simple. I will send data. You must confirm you received it. If you don't confirm, I'll send it again. This is how we achieve reliable communication over an unreliable channel. How stop and wait ARQ works. The sender sends one frame and immediately starts a timer. Then it waits. If the receiver gets the frame correctly, it sends back an acknowledgement. If the acknowledgement reaches the sender before the timer expires, great. The sender moves on to the next frame. But if the frame is lost or the acknowledgement is lost, the timer expires. The sender panics, a little grinning face with sweat, and retransmits the same frame. So the rule is clear: one frame at a time, no cheating. Sequence numbers, the smart trick. Now you might ask, sir, what if the receiver gets the same frame twice? Excellent question. To avoid confusion, stop and wait uses a 1-bit sequence number, 0, 1, 0, 1, and so on. This tiny number helps the receiver understand whether the frame is new data or a retransmission, preventing duplicate delivery. Small number, big responsibility. What the diagram shows. In normal operation, frame 0 is sent, ACK0 comes back, then frame 1 is sent. Life is peaceful. In the lost frame scenario, frame 1 gets lost. No ACK arrives. Timer expires. The sender resends frame 1 and finally receives ACK1. Problem solved. Pros and cons. Advantage: very easy to understand and implement. No headaches, no confusion. Disadvantage: very inefficient. Most of the time, the sender is just waiting and doing nothing. Only one frame can be in flight at a time, which wastes bandwidth badly, especially on fast networks. Final takeaway: stop and wait ARQ is like sending a courier and waiting at the door until they come back before sending the next one. Safe? Yes. Efficient? Not really. That's why it's important historically, but in real networks, we soon move on to smarter heroes like sliding window ARQ. Alright class, now say hello to a better hero. Go back in ARQ. This one is smarter and faster than stop and wait. Here's the idea. Instead of sending one frame and waiting, the sender sends many frames together, like answering multiple exam questions before the teacher checks them. This is called pipelining, and it uses a sliding window. The sender can send up to n frames without waiting for acknowledgments. Now listen carefully. The receiver is very disciplined. It only accepts frames in order. If frame 2 is missing and frame 3 arrives, the receiver says, "Nope, I was expecting frame 2," and throws frame 3 in the dustbin wastebasket. When frame 2's timer expires, the sender says, "Oops," and goes back, retransmitting frame 2 and all frames after it. That's why it's called go back in. Advantage: much faster than stop and wait because multiple frames travel together. Disadvantage: one small error can cause many frames to be resent, a bit wasteful, like rewriting the whole answer when only one line was wrong, grinning face with smiling eyes. So remember, go back in equals faster delivery, strict order, but dramatic overreaction to errors. Alright class, now we meet the ultimate hero of ARQ, selective repeat. This one is smart, calm, and doesn't panic. Here's what happens. Unlike go back in, the receiver here is very intelligent. If frame 2 is lost, but frames 3 and 4 arrive safely, the receiver says, "Good job, I'll keep these with me," and stores them in a buffer instead of throwing them away. No waste, no drama. Each frame gets its own ACK, even if it arrives out of order. When the timer for the missing frame expires, the sender retransmits only that one frame, not the whole group. Once frame 2 finally arrives, the receiver neatly arranges everything in order and delivers it to the network layer, like a teacher collecting answer sheets and sorting roll numbers before submission. Advantage: very efficient, no unnecessary retransmissions. Trade-off: needs more memory and logic, brains cost RAM. So remember, selective repeat equals smart receiver, individual ACKs, minimum retransmission, maximum efficiency. Alright students, let's finish this story with a final showdown. Think of these 3 ARQ protocols as students submitting assignments. Stop and wait is the very obedient student, submits one page, waits for teacher approval, then submits the next. Simple, but painfully slow. Go back in is faster, submits many pages at once, but if one page is wrong, the teacher says, "Go back and resubmit everything from there." A lot of wasted effort. Now comes the topper, selective repeat. This student submits many pages. The teacher keeps all correct ones safely, and if one page is wrong, only that page is corrected and resubmitted. So remember the table logic. Sender window grows from one in. Receiver window grows only in selective repeat. Out-of-order frames are discarded in go back in, but buffered in selective repeat. Efficiency increases, but complexity and memory also increase. In short, stop and wait equals simple but slow. Go back in equals faster but wasteful. Selective repeat equals smartest, fastest, but most complex. Think of channel utilization like a classroom microphone. If only one student speaks and everyone waits in silence, that's stop and wait. Lots of awkward silence, very poor use of time. The channel is mostly idle. Now imagine students speaking one after another smoothly. That's sliding window. No gaps, no silence, full use of the mic. Channel utilization simply means how much time the channel is actually carrying useful data. Delays, waiting for ACKs, and slow protocols reduce it. Sliding window protocols like go back in and selective repeat improve utilization by pipelining, keeping the channel busy. Alright students, let's bring theory into real life. Think of ADSL like ordering food at home. You mostly download, eat, and rarely upload, cook. That's why it's asymmetric. It runs on old telephone lines, which are noisy, so ADSL uses Reed-Solomon and CRC like spell checkers to fix mistakes before data reaches you. Now DOCSIS is like a big apartment Wi-Fi. Everyone shares the same cable, so the MAC layer acts like a strict society secretary, deciding who gets bandwidth and when. To handle noise and speed, it uses strong error control like LDPC, making cable internet faster and more reliable. So remember, ADSL equals phone line, individual connection. DOCSIS equals cable TV line, shared connection. Simple, practical, and straight from your daily internet life. Today, we explored how the data link layer works behind the scenes to make communication reliable and efficient. From flow control to error control, and from simple stop and wait to powerful selective repeat, we saw how protocols act like smart traffic police for data. We also connected theory to real life with ADSL and DOCSIS, proving that networking concepts are not just exam topics. They run the internet we use every day. Pushpin key takeaway. Reliable communication is not about sending fast, but sending smart. Thank you. And remember, every click you make travels through these layers before reaching its destination rocket.